dream do come true. Yeah,
Mr. Beamer, if we have a whole class, I think you have to give us all.
I think something different. I'm gonna give Lily
All right, we're going to talk about scalar surface integrals. So, remember from last time, whoops, I didn't mean to erase everything. From last time we said that for a parametric surface, given by R of U and V, that a normal vector to the surface is given by N equals R sub U cross R sub V. We cross those partial derivatives, those vectors. And the surface area differential, ds, was a magnitude of RU cross R sub V, du dv. So our surface area differential, the little piece of surface area, is a magnitude of the normal vector. And when we talk about vector line integrals, that's going to be important. And our surface area above a region, S, was the integral over the region of this magnitude of ds, R sub U cross R sub V, du dv. And R is the region in the UV plane. So that's just a quick recap of what we talked about last time. And if z equals f of xy, if our surface is given in z equals f of xy, then ds was the square root of f sub x squared plus f sub y squared plus 1 dA. And we realized that this was the magnitude of del G dA if capital G is f of xy minus z. All right. So that's what we talked about in our last lesson, kind of in a nutshell. Now, when we talked about line integrals, we defined a scalar line integral. Scalar line integral, we said that was along a path, f of xy ds was the integral from a to b, f of r of t, so we parameterize our curve, and then times the magnitude of r prime dt. So what we're doing here is we're multiplying some function value times a little piece of area, and then we're summing that along the curve. Not a piece of area, a piece of length. We're summing that along the curve. So we could interpret the function as a mass per unit length, the charge per unit length, something like that. We could also interpret this as an area. If f of xy, we visualize that as a surface above our curve, and f of xy gives us the height that we're above the curve, and this integral would give us the area, that lateral area below that curve, or above the curve, below the surface. So we're going to do something similar with scalar surface line integrals. So what we want to do for a surface we have a function f of x, y, z. And we could think of that function as a mass per unit area, charge per unit area, the blue pixel saturation per unit area, some function of the area. And we're going to multiply that by our little piece of area, ds. So if we think of this as a mass per unit area, we multiply that by the little area, we sum over the surface above some region in the xy plane or the uv plane, and we get the total mass of whatever the material is that's making up the surface. If it's a charge per unit area, we'd get the total charge that's on this surface above a particular region. So that's our idea here. And we're going to define it exactly the same way. So our scalar surface integral. Our scalar surface integral is going to be the way we write it as the double integral S for surface of f of x, y, z ds. And the way we're going to evaluate this is going to be the double integral above some region in the UV plane. And we're going to express f in terms of our parameterized surface, r of u v, times the magnitude of Ru cross R sub v du dv. So we're making the exact same definition for a surface integral that we did for a scalar surface integral that we did for a scalar line integral. And let me just make this f of R of u and v is f expressed in terms of the parameters. And ds is this quantity. And R is the region in the UV plane. So we have a surface above some region in the UV plane. And this is how we're going to evaluate our integral. And again, if z equals g of xy, then ds is the square root of g sub x squared plus g sub y squared plus 1 dy dx. And f of x, y, z is going to be f of x, y, g of xy. Because our surface integral is a double integral, so we need two variables, not three. And here the region, R would be our region in the xy plane. So for a scalar surface integral, we're just multiplying some function times a little area on the surface and summing that over our region in the plane. Now what we're going to do tomorrow for vector line integrals is we're going to sum the normal component of a vector field times the area over the surface. And that's going to give us this idea of the flux, how much stuff is flowing out of the surface. And that'll be how we define our vector line integral. All right, questions so far? So really all we're changing from what we did last time for finding surface area is we're just putting a function in here. And we have to express our function in terms of our parameterized surface, if it's the parameterized surface, or we express our function in terms of x, y, and the function on our surface. We want what f of x, y, z is on that surface. Whoops, do I need another parenthesis here? Yes. Okay. All right, so let's set up a couple of these. So the way that you will see these is evaluate, or one way that you'll see them. Double integral over our surface of x minus 2y plus z ds, where s is z equals 15 minus 2x plus 3y, 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 4. All right, so let's look at this piece first. So from this information, what is our surface? Surface is a plane. Z equals 15 minus 2x plus 3y. What is this 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 4 telling us? This tells us the region R in the xy plane. So we need two pieces of information. We need to know what our surface is, and we need to know what the region is in the xy plane.
Will they give you the region?
Somehow you'll have the information to get the region. So if it were like an upside down paraboloid above the xy plane, you'd know the region in the xy plane was a circle. So somehow you have to be able to figure out the region, otherwise you can't set up your integral. And this is our function, x minus 2y plus z. So that could be the mass per unit area of this plane, the charge per unit area, something like that. All right, so here we have z equals g of xy. And we need our partial derivatives. So what function do we take the partial derivatives of? We need to take the partial derivatives of the function that represents the surface, because we want that those partial derivatives, what we talked about last time, that's giving us a normal vector. The surface is what we take the partial derivatives to get that quantity square root of g sub x squared plus g sub y squared plus 1. So we take our partial derivatives of our surface. So g sub x is negative 2. G sub y, this is nice and easy, equals 3. So ds, our little piece of area, is going to be the square root of negative 2 squared plus 3 squared plus 1 dy dx, or dx dy. For this one, it doesn't really matter. So that gives us a square root of, what, 9, 13, 14? And our function, now we have to represent our function. I'm going to call this g of xy. And this is going to be f of xyz. We need to find what our function is on the surface. On the surface, z is 15 minus 2x plus 3y. So f on the surface is x minus 2y plus 15 minus 2x plus 3y.
You just plug in Z.
Just plug in z.
It's okay to mix those two, g of xy and f of xy.
Yes, because what we're doing is on the surface, everywhere on the surface, z is 15 minus 2x plus 3y. So that's going to give us that function value just on the surface. So we get, when we simplify this, minus x plus y plus 15. So our integral is going to be the integral from 0 to 2, the integral from 0 to 4 of this quantity minus x plus y plus 15 times the square root of 14 dy dx. Easy integral to evaluate, and we end up with 128 square root 14. All right. Questions? All right, let's look at one that takes a little more work.
Mr. Beamer,
Yes.
important information.
Yes.
Today's Gauss's 241st birthday.
Wow.
Wow.
We're going to be talking about Gauss's law in just a couple of days. Yeah, that's going to be fun.
Very useful.
All right. So I want to set up one. I want to set up one with a parametric surface, and then we'll do a setup with a little that's a little more involved. So for a parametric surface, we want to evaluate double integral or surface integral f of xy ds, where f of xy is x plus y, and s is given by r of u and v to cosine u I hat plus 2 sine u j hat plus v k hat. And 0 less than or equal to u less than or equal to pi over 2. And 0 less than or equal to v less than or equal to 2. All right, so first off, what is that surface? Cylinder, but first quadrant. So it's a quarter of a cylinder. And this 0 less than or equal to v less than or equal to 2, that's the height of the cylinder. So our surface is this quarter cylinder from the xy plane to 2 units above the xy plane. This is our function that we're multiplying times a little bit of area, maybe mass per unit area, charge per unit area, something. All right, so we need our normal vector, magnitude of our normal vector. So r sub u is minus 2 sine u I hat plus 2 cosine u j hat, and r sub v is just k hat. And then we need r sub u cross r sub v. So we do our determinant, I hat, j hat, k hat. And we have a 0, 0, 1. And when we do that, when we find our cross product, we get 2 cosine u I hat plus 2 sine u j hat. And the magnitude of this is 2. And then we need to express f in terms of our parameterized surface. We want to know what f equals on the surface. So f of r of u and v, well, x is 2 cosine u, and y is 2 sine u. So on the surface, x plus y equals 2 cosine u plus 2 sine u. So on that quarter cylinder. And this gives us our region in the UV plane. So this is really polar coordinates, right? Or cylindrical coordinates. So we have integral from 0 to pi over 2, integral from 0 to 2 of 2 cosine u plus 2 sine u times this magnitude, 2, and the order that I set it up here was dv du. Easy integral to evaluate. Be careful with this one, because the sign and when you get your cosines and the signs at the end, they have values at 0 and at pi over 2, so it's easy to forget that. And when we evaluate this, we end up with 16. Seems like kind of a boring number for that surface. Right. Uh-huh.
You're given a surface in terms of x, y, and z. Could you always, and then there's one z, you could always find it if z is equal to g of x, y.
Right.
Alright.
Right. Yes.
So why have we gotten rid of the little like component notation for vectors and gone to I hat?
So that's a good question. Curious of why do we get rid of component form of vectors with the little angle bracket, and we're using kind of exclusively I hat, j hat, k hat? Really, the reason is that historically, all of this was developed. All of this stuff that we're doing was developed to describe electromagnetism.
And then use I hat.
And in physics you use I hat, j hat, k hat. So it's kind of traditional.
But it's not incorrect.
It's not incorrect.
Angle
No,
brackets because
it's not as incorrect to use angle brackets. It's more traditional because this was developed as the language for electromagnetism. So, as interesting, I'm reading a book about the history of analysis in the 19th century and how the development of potential theory is what we're talking about led to all kinds of discoveries in complex analysis and elliptical functions and that kind of thing. So all of this stuff was kind of developing all together.
So which one is better, I hat, j hat, k hat, or angle brackets? Just
I think the angle bracket one is a little more compact, and but you'll see that more in math notation. And actually what you'll do, what you'll see in math is you'll see vectors represented in terms of matrices,
Yes.
and as more in a linear algebra. Yeah.
Is the angle brackets like the matrix?
Well, yeah, angle brackets usually, and then they do the a row vector or a column vector for a vector, or a row matrix or a column matrix for a vector. All right, let's look at one where we have a little more intricate setup. All right, we want to evaluate our surface integral, f of x, y, z, ds. For our function is the square root of x squared plus y squared plus z squared. And our surface is z equals the square root of x squared plus y squared, comma, x minus 1 squared plus y squared less than or equal to 1. All right, so let's pick out our pieces of information. What is our surface? What's that? This is a cone, right? And it's an upper cone because we just have the positive square root. What is this second piece telling us? It's we're interested in the portion of the surface above that circle in the xy plane. Or you could think of it as being inside the portion of the surface inside this cylinder, where this is the description of the cylinder. So this gives us our surface. This gives us the region in the xy plane. And just based on this setup, how do you think we're going to want to set up this integral? Just the way the functions are described. Polar, right? This is a circle. We have a square root of x squared plus y squared, square root of x squared plus y squared plus z squared. We have all those square roots of things squared. So that suggests polar coordinates. So we're going to talk about polar coordinates. The surface is a cone, and it's above this circle in the xy plane or within this cylinder. So our surface z, this gives us our surface. So that's where we're going to get our partial derivatives. dz dx for our partial derivatives for our little area increment ds. dz dx is x over the square root of x squared plus y squared. dz dy, symmetrical, so we get y the square root of x squared plus y squared. Pretty common derivative. You'll see that a lot. So our ds is going to be the square root of, I need to make my square root bigger, x over square root of x squared plus y squared squared plus y over that same square root, x squared plus y squared squared plus 1, and this would be dy dx or dx dy, since we're setting up our region in the xy plane, or when we're going to go to polar coordinates already paid. What does this come out to? It looks ugly now, but it simplifies pretty nicely. We get a common denominator of x squared plus y squared, so we get 2 x squared plus y squared over x squared plus y squared, so we just get square root of 2. And we need f. We need our function on the surface. Is f equals the square root of x squared plus y squared plus z squared, x squared plus y squared. So we get square root of 2, square root of x squared plus y squared. So finally, we have the double integral over our region in the xy plane of 2, because we get a square root of 2 here and a square root of 2 here, and we get a square root of x squared plus y squared dy dx. Now our region in the xy plane is that shifted circle. So let me draw a little picture here. Let's see, we have a radius 1. We're shifted 1 unit on the x-axis. There's our region in the xy plane. Now we can go through the process of changing these to polar coordinates. Anybody remember what the equation of that circle is in polar coordinates? What is it? R equals cosine theta. And what is that? Goes traced once on 0 to pi. All right, you could get to the same place by plugging in our cosine theta here and our sine theta there and doing the algebra and simplifying, and you get r equals cosine theta. All right, and our theta value. So 0 to pi, because we're going around once. So now we can set up our integral. Yeah, we can write now. We have 2, integral from 0 to pi, the integral from 0 to 2. Is it r cosine theta or is it 2 cosine theta? Did I write this? So this would be diameter of 2, right? Because we're shifted over 1 unit, so the diameter would be 2. So this would be 2 cosine theta. The number in front of that is the diameter of the circle. All right, 2 cosine theta. And again, if you didn't recognize that, you can go through, substitute r cosine theta here, r sine theta there, set it equal to 1, solve that equation, simplify. And then our integrand is just r times r dr d theta. So we get 2 integral from 0 to pi of r cubed. I'm going to put a 3 out there. R cubed from 0 to 2 cosine theta d theta. So that's going to be 2/3 the integral from 0 to pi of cosine 8. So I'm going to make that a 16. Cosine cubed theta d theta. The 2 cosine theta cubed. So we had to cube that. All right. What is the period of cosine to the 3rd theta? What's the value of cosine theta at 0? 1. What's the value of cosine theta at pi? Negative 1. There's still negative 1. What's going to happen if we integrate that from 0 to pi? We're going to get 0. Can we get 0 here? Because we can't, because f is always positive, right? Square root of x squared plus y squared plus z squared is always positive. Our surface, ds, is always positive. So we can't get unless everything is 0, happens to be 0 all over the entire surface, we shouldn't get a 0 result. So what do we do? What's that? Yeah, just can't we integrate from 0 to pi over 2 and multiply by 2? When we have a periodic function, we can always divide things like that. So it's going to be 32/3. The integral from 0 to pi over 2 of cosine to the third theta d theta. We don't want a 0 result.
Why can we divide it? Because isn't the function above that surface, it's not constant. It's not a constant height above it the entire time.
No, it's not. So we're at this point we're not. This isn't the height of a function above a surface. Yes.
So do you just kind of have to like recognize that as you're doing a problem? Like,
Well, if you continued and you got 0, that should tell you, oh, I shouldn't get 0, and then you back up and go from 0 to pi over 2.
would always
Why
be
does that fix
0?
it? Is that just like
It's like a thing saying we have positive area and negative area.
okay.
But we're interpreting this as a physical quantity.
Thing, and
Right.
Says it's okay.
Now and we're looking at this and we see that this is always positive and this is always positive.
We know it should always be
It should be we should be multiplying positive things unless we're multiplying 0 all over the surface.
So it's an error introduced by converting it to a
Right. Now, if f of xyz represented a charge and it was not always positive, so charge per unit area, and this f of xyz was not always positive, you could integrate that and get a 0 result, saying that the total charge on that surface was 0 because you have the same amount positive as negative. So you have to be a little careful with this.
Maybe a quick question.
Yes.
My calculator says that doesn't evaluate to 0. Does the calculator just know that already and split up into 2 integrals? I mean,
Are you
cosine.
Yeah.
That's a good question though.
There you go.
Okay, now it evaluates to 0.
Some
All right.
programs will automatically
Some will, yeah. Or they'll tell you, do you get a 0 result? Is that what you want?
Yeah, MATLAB will tell
Right.
you, it will give you the 0 result and then say non-0 result, or it'll say 0 result and then have an option for non-0 result.
All right.
2
Now we've settled that. Now we're on to the straight evaluating integrals. How do we evaluate cosine to the third theta d theta?
minus sine squared.
Ah, yes. 32/3. Integral from 0 to pi over 2 of 1 minus sine squared theta. Cosine theta d theta. And then we end up with a cosine theta and a sine squared theta, cosine theta d theta. So we end up with 2 integrals. So not now we can evaluate this. This is just a u sub. And we get 32/3 times, when we evaluate this, we get 2/3. And we get 64/9. Yeah.
So it is just error introduced by converting to polar coordinates. So anytime you switch the method of integration, you add a likelihood that this can happen.
Well, and otherwise, if we didn't change to polar coordinates, we would do a trig sub, and you'd still get sines and cosines, and you'd probably end up in the same place. Right, right,
There's a lot more work.
right, a lot more. All right, questions? Okay. That was a really nice example. Oh my God.
Calling people out already.
All right, we don't get many assignments like that.
That's the thing, these were the only ones this year where it was that huge list.
Humor, I can't handle it.
1 to 5.
What happened to our list?
Dude, 3 to 5.
No.
Yes, I know, Brody.
Every
Now,
other.
it really bothers my other classes when I say something like 1 through 21 even.
Why?
They're like, where do we, which